So we're going to start this lecture by defining what it means to be an interval. So a subset of the real numbers is an interval if whenever A and B are both in I, and there's a number R that's between A and B, we have that R is also in I. So those are what the things we care about. So here is lemma 1.6. So this says that all the intervals all have the following forms. So you've got what we know as open intervals, what we know as closed intervals. We've got half open intervals. Half open on the other side. And those are all the bounded intervals. And then you've also got the unbounded intervals. This what ends an open set. This one's a closed set. Another open set. Another closed set. You've also got the doubly infinite interval, better known as all of the real numbers, and the empty set is also technically an interval. Sometimes people define intervals to be non-empty, but consistent with the definition we've given above, the empty set is an interval. And then furthermore, all intervals take one of the above forms. For some A, B real numbers with A less than B. So that's really what we need to prove. So it should be pretty obvious just by inspection that I guess that is 10 and possibilities. I've written down that all of those are intervals. Everything written in lemma 1.6.6 is an interval. Now let's see why the converse is true. So let's prove this thing. So let's prove the converse. Let's let I be an interval in the sense of the definition written at the start of this video. And let's let alpha be, and notice that I is a set of real numbers, so let's let alpha be the infimum, the greatest lower bound. And if I is bounded below, then it has an infimum. We can just, if it's not bounded below, that is, if there are elements of I that are as small as you want, as negative as you want, we can just let alpha be negative infinity. And similarly, we're going to let beta be the supremum. And then if we allow alpha, if we allow plus or minus infinity, then alpha and beta, they have to exist. And I claim that it is enough, that is, suffices to prove that the open interval with lower endpoint alpha, higher endpoint beta is contained in I. Because alpha is the infimum, beta is the supremum. Either I is just this interval from alpha to beta, or you throw in one of the endpoints, and that gives us one of those 10 things written as intervals. One of those 10 possibilities in lemma 1.6.6. I suppose you might want to think about the special case of the empty set, but that's fine. We can do that. So now let's just let x be in this interval from alpha to beta. So that is, alpha is less than x is less than beta. So, and remember, beta is also known as the supremum of I. X is less than the supremum of I, so that means x is not an upper bound. For I, that means there is a b in I with b bigger than x. And similarly, x is not a lower bound for I. That means there's something less than x that's in I. There is an a in I with a less than x. A, b are in I. A is less than x is less than b. So by definition, of interval, we have that x is in I. So that tells us that if I is an interval in the sense of the definition given above, then I contains this open interval from alpha to beta, and then maybe we throw in alpha, maybe we don't, maybe we throw in beta, maybe we don't. But in any case, we get one of these, 10 cases. So that's how we show that intervals, as you know them from your past classes, are the same as intervals with this definition I've given you, which may be a little funny looking, but is a lot simpler than just listing out the 10 cases. And here is your homework 14. This is exercise 1.6.5 in your book. If I, J are two intervals, then either they are disjoint, that means there are no points between them, or their union is an interval. It's actually possible for them to be both. If, say, I is an open interval and J is a closed interval, they can be disjoint and their union still an interval, but if they overlap at all, their union definitely has to be an interval. And I'm not going to prove that to you because that is your homework for 15, but we are going to need to use this fact for the next result. So let's let G be a subset of R. Then any subset of R is open if and only if G is, you can write as the union from K equals 1 to N IK, or if it's the union of countably many, so either finitely many or infinitely many, but still countably, where each IK is open and any two of them are disjoint. So what this looks like is any open set in the real line. It looks like you've got it looks like a bunch of patches like this. Maybe you've got infinitely many of them, maybe you've got countably many of them, but it looks like a bunch of intervals that are separated from each other. So let's prove this. So the first thing I want to do is clarify slightly this issue of supremum, of what exactly the supremum means for unbounded sets. So we're going to generalize the supremum of E, that is, we define sup E to be, we're going to have three cases, and we're going to say it is the least upper bound for E. And that's if E is bounded above and also E is not equal to the empty set. We're going to say that the supremum of E is infinity if E is not bounded above and then this one may seem a little strange. We're going to say that the supremum is minus infinity if E is equal to the empty set. And now that may be a little strange, but notice the empty set, you pick any number you want. It's bigger than all the elements of the empty set. There aren't any elements in the empty set, so none of them can be bigger than the one you want. So every real number is an upper bound for the empty set. Therefore, the least upper bound, if you allow yourself infinity, is indeed minus infinity. And we define the infimum similarly. It's infinity if E is empty. It's minus infinity if E is not bounded below. And it's the greatest lower bound. In all other cases, that is, if E is non-empty, but it is bounded below. So once we've got those definitions under our belt, we're going to pick an open set G, and we're going to show that G is the union of countably many disjoint open intervals. So let's let X be an element of G. And let's define A sub X is going to be the supremum of the set of all Y such that Y is not in G and also Y is less than X. And B sub X is going to be the infimum of the set of all Y that are not in G and that are greater than X. Notice that A sub X is the supremum of a set that's bounded above. X is the upper bound, so the supremum A sub X, it's got to be either a finite number or if this set has any elements at all, or it's minus infinity. Yeah. And similarly, Bx is either a finite number or plus infinity. Let me draw you the picture of this. Here is our number line. Here is our set. Here is G. Let's say here is the point X, and then you just take and then your A sub X is going to be here. And if by chance your set G happened to be half infinite, if everything less than X happens to be in G, then your A sub X is in this case is not located here. It's a sub x is minus infinity in this case. And then we're going to give this a name. We're going to name j sub x. We're going to say that is a sub x, the interval from a sub x up to b sub x, the open interval. And in this case, that would be from minus infinity up, including x, up to b sub x. And so I want to tell you three things about this interval j sub x. So the first of them is that x is in j sub x. So the point is x can't be a sub x, but it's got to be bigger than it. Can't be b sub x, got to be less than it. Second thing I want to claim is that j sub x is a subset of g. Suppose, why don't I go ahead and say j sub x is an open interval. And the fourth thing is pretty straightforward, is that j sub x is the largest set that's satisfying that satisfies the above three conditions. And what I mean by that is that if I've got an open interval, say AB, that contains X and is contained in G, then AB is contained also in J sub X. So it's not, J sub X is not only longer than AB, it in fact contains AB. So now here is the proof of the claim. So the first thing to notice is that this set, the set that AX is the supremum of, X is an upper bound. And similarly, X is a lower bound for this set at BX. AX is supposed to be the supremum, that means the greatest upper bound, the least upper bound, and X is an upper bound, so we've got that AX is less than or equal to X, is less than or equal, and X is less than or equal to BX, because X is an upper or lower bound. Okay, so to show that X is in JX, we have to show that X is not equal to AX. So by proposition, let's see, 1.6.4, there is a positive number epsilon such that some interval x minus epsilon, x plus epsilon is contained in G. So that means if y is bigger than x minus epsilon, either it's in this interval or it's bigger than x. So we're left with so AX can't be any bigger than X minus epsilon, and X plus epsilon can't be any bigger than B sub X can't be any smaller than X plus epsilon. If we go back to our picture here, remember, I'm running out of colors. We've got this little interval around X that's inside B. And so we see that the smallest y that's not in G and bigger than X, you have to go at least up to X minus epsilon to get there. So we have that X is, so in particular, AX is strictly smaller than X is strictly smaller than BX. So X is in our interval JX. And also note that AX, that gives us that AX is strictly less than BX as well, so JX is an open interval. That's true by inspection. It's not an empty set either. So now let's move on to showing that JX is contained in G. So let's say that Z is in JX. That's AX, BX. So either one of the following things is true. We've got that AX is less than Z. We've got that either Z is less than X, or Z is greater than X, or I suppose Z equals X, which we've already seen is in J sub X, which by assumption, is in our open set G. So in the bottom case, we see that Z is in G, and remember, we're trying to show that Z is in G no matter what element of J sub X it is. So in the first case, remember, if Z is in this interval, it's got to be bigger than A sub X. And in the second case, it's got to be less than BX. And then if we go back to our sets where we defined AX and BX, we see that if Z is less than X, then, and it's also bigger than AX, then it can't be in the set A is the supremum of. So that means that Z is in G. And similarly, if Z is less than BX, that means it's less than all the numbers that aren't in G and are bigger than X, so it can't be a number that's not in G and is bigger than X, so it must be a number that is in G. So in any case, we've concluded that IX is contained in G. So that gets our first three claims out of the way. Now I'm going to point out something to you, and that's that AX and BX aren't allowed to be points in G. So if Y is in G, then we've got some little interval that's contained in G around Y. And if I suppose I should have called this something different, if y is greater than or equal to z for all z in the set that we defined x with, all if it's bigger than all z that are not in G and also less than x, then so is y minus epsilon, because there's nothing because everything between y and y minus epsilon is in G. Yeah. So we have that y minus epsilon is the smaller upper bound, so ax can't be any bigger than y minus epsilon, so y is not equal to ax for any y in G. So ax is not in G, and similarly, we could make the same argument, and I'd really like you to get out of the habit of repeating identical arguments. Bx is not in G. And if you've got an interval AB that contains x, and AB is not contained in the interval from AX to BX, either you've got a point that's smaller than AX that's in your interval, or you've got a point that's BX or bigger. And so then one of your endpoints, not contained in, not a subset, then either you've got AX in AB or BX in AB, and whichever it is, in either case, AB is not a subset of G. It's got the point AX or BX, and neither of those are in G. And this is going to show that, and that gets the last part of our claim. That shows that JX is indeed the longest open interval that has X in it and is contained in G. Now we need another claim, and the other claim is, let's let X and Y be 2 points in G. And we claim that either JX is the same and JY are the same interval, or their intersection is empty. And the proof of that actually follows pretty straightforwardly from actually your homework. So let's go ahead and sketch the picture. Here is the point X, and here's JX. It's an interval about X, and the endpoints are not in G. And then here is the point Y. So either you start out and then you draw your interval, and there's this point here that's not in G, so you can't go any further than that. So JY and JX can't intersect each other. Or the other possibility is that you start out with a y that's in this interval, and then when you build up your biggest interval containing y, of course, you get the same interval back again. So the proof, let's suppose not. Let's suppose that the two sets are not disjoint. Jx intersect jy is not the empty set. And then by exercise 1.6.5, if you've got two intervals that are not disjoint, their union is also an interval. So x is in jx union jy. Jx union jy is contained in G because it's the union of two things that are each individually in G. And jx union jy is open by proposition 1.6.3. So jx union jy, it satisfies all the conditions of jx. It has x in it, it's an open interval, it's contained in G, and so we have that jx union jy is contained in jx, so in particular jy is contained in jx. And then similarly, jx is contained in jy, so jx equals jy. And that completes our proof of this claim. So now let's try to put this all together. Let's let E be the following collection of open intervals. It's the set of all jx such that x is in G. Then E is a set of open intervals and if I and k are two intervals in E, then either I equals k or I intersect k is the empty set. And finally, we have at each I in E is a subset of G, is one of these J sub x's, and if x is in G, then x is in J sub x is in one of the intervals I. So we have that G is the union of all I and E. Each I is contained in G. Each x in G is in one of the I's. So we've got that G is the union of a bunch of intervals that are open and pairwise disjoint. So now we just need to show that there are only countably many of them, and we'll be done with this proof and also done with this video. So, first thing I am going to point out is that every open interval contains a rational. And the proof is straightforward. All right, that is every non-empty open interval contains a rational. Let's name the open interval something. Let's name it I. We let x be at any point in I. Then x minus epsilon, x plus epsilon is contained in I for some epsilon bigger than 0, and by theorem 1.2.28, we have that there is a rational number with x minus between x minus epsilon and x plus epsilon, and so Q obviously has to be in I. So let's get back to countability of this collection of sets. So let's let F go from Q to the natural numbers be a bijection. We know we saw in section 1.5 that the rationals are countable. Weird but true fact about countability. So we know that some such F exists. Let's let G go from E to the natural numbers be as follows. We're going to say that G of I, that is G of an interval, that is going to be the minimum, also an infimum, of f of Q such that Q is in I. So here is the picture. There's your number line. Here is your interval I, and then we're going to say we've got, let's say, our first rational is here, our second rational is here, then we've got Q3, Q4, fifth rational is here, sixth rational is here. Then the first one that wound up in I was 3. So in this case, we've got that G of I is 3 for this one. So this is how our function works. And then remember that every set of natural numbers has not only an infimum but a minimum of the smallest element. And I claim that G is 1 to 1. And it's not going to be on to, but here is how you show that G is indeed 1 to 1. if g of I equals g of k, and let's give it a name. Let's say gi equals gk equals m. Then I feel like I should clarify my notation a little bit here. We've got that f is a function from the rationals to the natural numbers. So f of q1 is 1, f of q2 is 2, and 3 is f inverse of q, and q3 rather is f inverse of 3. So then f inverse of m is a rational number. It has to be in both I and k. That is, so q sub m is in I, and also q sub m is in k. So I and k are not disjoint. So I equals k. And this completes the proof. Thus, our set E is countable, since G is a one-to-one function from E into the natural numbers, and if there's an injective function from a set to the natural numbers, then that set has to be countable. And we saw already that G is the union of all the intervals in E. So this completes the proof.